Welcome to our Parallel Programming Concepts course. This week we talk about accelerators, and in this unit we talk about the future trends in accelerated computing. First of all, accelerated computing was intended to support accelerators on the one hand side and general purpose on the other hand side, and since we've now seen it everywhere, even in embedded computing, there is a trend towards more platforms. And the first platform that everybody is using basically every day is the web browser. And for this platform, a WebCL standard is on the go. So at the moment it's in the draft version phase, but there is already a number of implementations showing that it's possible. And the idea here is that every web browser can access the underlying accelerators in order to speed up its tasks. And with such a system, we could see compute-intense physics engines or video editing live in the browser. And in addition to this, we also see a trend towards embedded devices like mobile phones. And there is already also a client driver extension for mobile phones. So for your mobile phone, you are allowed to query all the OpenCL implementations that are on the phone. Currently, there are not many implementations, but this is something that we will see in the future. So support for browsers and support for devices as well, in order to get the full performance of the built-in accelerators. Then there's another problem. We already talked about problems that can be solved with accelerators, and usually we have this static index grid that allows us to subdivide the problem that we have and throw the indexes on it in order to do the data parallel calculation. And there we have the choice between having a very gross grained overlay and a very fine-grained overlay. And if it's too coarse-grained, then we only have a very small amount of threads. And as we've already learned, having a small amount of threads is always a bad idea, because then you cannot leverage the full performance of the parallel units. So usually you want to have a lot of parallel tasks, like on the right-hand side, but then, as we see in the picture, a lot of those doesn't have to do anything, right? There's so many parts of it that are only white. So what we actually want to have is something like on the right-hand side, where we have a dynamic grid, and let's say we create a coarse-grained field, and then for all the parts of the field where we really find some work, we spawn more threads to actually do this work. So we start with a small amount of threads, and then we dynamically increase the amount of threads to work with those fields. And this is very different from what accelerators are currently capable of, because they have the SIMD execution fashion. And especially what we had to do in order to achieve this currently was to start a very coarse-grained grid on the GPU from the CPU, then get the results back to the CPU, then the CPU decides, oh well, we have to do more, and he creates a finer-grained grid and lets the GPU execute it, and afterwards he has to analyze this result again in order to see where there's still work to do, and then he creates a new grid on the GPU, and so on and so on. So there's always this communication between CPU and GPU all the time. And now, with this dynamic parallelism idea that is already part of the OpenCL standard in the second version, so OpenCL standard 2.0, we have this new functionality where the GPU itself could spawn those grids, or those new workgroups, basically. And this is what we see on the right-hand side. So the CPU starts the processing on the GPU finds that there's more work to do for parts of the data range of the grid, and then it creates new workgroups working on this. And finally, when everything is done, it copies the results back, and the computation is continuing. And this means that the CPU, instead of orchestrating the GPU all the time, can do some other useful work, for example. So with this kind of approach, we can create those grids and this behavior, and thereby getting rid of a lot of threads doing nothing basically, and increasing the amount of threads which are actually doing something useful, and also having a way to sizing the work groups so that they all have kind of the same amount of work. And what, as I said, is already part of the OpenCL standard, but somebody has to implement it, right, so that we can use it. And NVIDIA actually did this with their Kepler architecture. And in the old graphics cards, we didn't have the possibility to do this because there was no way the GPU could create new workgroups. You had always to create new workgroups on the host, because the host was actually creating the queues that the GPU was using. And with the Kepler architecture, they introduced a grid management unit right on the GPU so that the GPU itself could create new work units on the fly. And this new piece of hardware on the GPU allows to leverage this dynamic programming functionality, dynamic parallelism functionality. Okay, so as we've seen, OpenCL is pretty elaborate. We have to write a lot of code in order to achieve what we want. But as I said before, it's just a fundamental thing where other programming languages should build upon. And this is actually what OpenACC did. OpenACC looks a little bit like OpenMP that we've already seen. And the idea here is, as for OpenMP, that you just put some small pragmas in your code, and then the runtime is taking care of putting those parts onto the accelerator. And the first thing would be to copy data onto the GPU, and we just say accelerator data copy and what parts we need to copy. This would be like the whole copying stuff to the GPU thing that you had to describe yourself by hand before. And then we just say OpenACC parallel for the for loop, and then the runtime will automatically parallelize it. And at the end of the for loop, it will collect all the data. And the beauty here is that you don't have to cope with all the details, but you can just write this in your code and then it will basically work. But still, as we learned before, in order to achieve really good performance, there's a lot of things that you should tweak in order to get this performance. And for example here, a new is copied to the GPU, but actually it's only written on the GPU, so it would be sufficient to just create it there and then have the GPU fill it, instead of filling it at the CPU side with zeros and then copying it there. So OpenACC actually allows this. You can say, okay, well, I want to copy A to the GPU. I want to create a new array, a new on the GPU, and then I want to work on this. They also allow for more sophisticated solutions like reduction instead of doing the loop yourself. Reduction is allows, so if the runtime knows that it's a reduction instead of just arbitrary work, then it knows how to parallelize this in a more clever fashion. Actually, you could write this reduction yourself, but it's very complicated compared to just using one reduction keyword, right? And then you can also say with the gang and worker keywords how big the work groups should be, how many workers should be in a work group, and how much work you have all in all. So here this would mean I have 32 work groups and 16 workers in each work group in the first case, and in the second case you would have 16 work groups and 32 workers in each work group. Yeah. So this way it's pretty easy to get to the GPU without all this overhead, and the runtime takes care that the GPU is selected. And also, and this is very helpful as well, if the runtime figures out that this won't run on the GPU at all because you use reduction or something else that the GPU is not supporting at the moment, then this code will be run on the CPU instead. So the runtime takes care that this will actually be executed using whatever it finds to be good enough in order to execute it. This is also very convenient because otherwise you would have to take care of this yourself. So the final question would be, how will future computer systems look like? And the answer is pretty much like what we see with phones already. We have a very hybrid system. So we could have two CPUs, and one CPU would have more cores than the other one, or the cores would be faster than the other cores. We could have Intel Sandy Bridge, like the CPU below, where we have cores and a GPU already on the CPU. We could have dedicated accelerators like a GPU or the Intel MIC accelerator, and they all are built together in one system. And as a programmer, in order to really speed up our system, it would be great if we could use all those computational power in the system. And this is a very demanding task, and we have those programming frameworks like OpenCL or OpenACC in order to help us do this and achieve this. Okay, so this week we learned that accelerators are promising a big speed up for you, especially for data parallel applications, because they actually have the SIMD execution model, which means that all the tasks are basically doing exactly the same but on different data. This is very fast for data parallel applications if you have no branching. And you can have thousands of threads running exactly the same instructions on the data because they are so lightweight on the GPU. And one thing is very different on accelerators. They have this memory latency hiding approach instead of the caching approach that we have with CPUs. So here we have a huge amount of lightweight threads that are all stored in the CPU at the same time, and you don't have the costly context switch that you have with CPUs. We've seen that there's an enormous diversity on the accelerators, and OpenCL aims to be the standard model for all of them. So you could have one understanding of all the accelerators and use one programming model in order to use them all. Therefore it introduces uniform terms, compute device for this board, compute unit for basically a processor, and then processing elements for the cores. The fundamental idea is that you have a loop, which an independent body anyway, and then you just map that onto an index range. So instead of iterating over the whole loop, you just put it into chunks, and then the chunks are executed on the GPU or other accelerators. Kernels, therefore, are written in C. Actually, a subset of C, because some parts are not allowed, with some extensions to C in order to leverage the fundamental architecture of those accelerators better. You compile those kernels at runtime, which is an interesting thing because you could actually optimize and tweak them on the system where you want to execute them. So instead of the old model where you compile something and then it runs on all x86 architectures, here you compile it at the runtime, and this means that your code actually can support future accelerators that are not on the market already. Okay, so you could create it in a way that the kernel is modified before it's executed, and then it could be really tailored to the accelerator that you find in the system. And then those kernels are executed in parallel by all those threads that you have on the accelerator. Accelerators have a complex memory hierarchy that you have to keep in mind. This local memory, for example, is way faster than the global memory, but you have to take care of it yourself. And some of the old promises, like cache coherency on CPUs, are not there anymore for GPUs, so you really have to take this into consideration when it comes to correctness of your algorithm. Getting to the GPU is fairly easy. Getting things fast is fairly hard because you have to know all those optimizations that you can do, and we've introduced you already to some of the best practices for accelerators, but still it's very helpful to have a good understanding of the hardware characteristics that you are working with. That, on the other hand, you can use in order to create a kernel that's actually perfect for this accelerator. In the future, we will see faster accelerators with way more features, more platforms that are supported, and a better programmability. So this is really a future we can look forward to. And since we've heard so much about multi-cores and many cores already, the question for the week is, what if my computational problem is still too demanding? If we still need more power in order to solve this, what can we do then?